All right, so in this workshop, we're going to learn how to make an XLR cable. And along the way, we're going to learn how XLR cables work, and we're also going to learn how to solder. That's just part of the process. So this is a cable that I actually made, and it works. Check, 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 1, 2, 3. It works very well, actually. But how does it work? Well, I'll unscrew it for you and I'll show you the inside. And I'm going to explain a little bit about how this is wired and the reasoning behind it. And then I'm going to show you how to make it. So you've got this strain relief here. It should just pull straight through. There we go. So we've got these 3 wires in here. There's actually 5. I'll explain more about that later, but you basically got like a blue line there and a white line, and then you've got this braided shield that's been twisted together into a wire. So you've got 3 different wires. This is called a balanced cable. Not all cables have 3 wires. Most cables are actually unbalanced. They only have 2 wires. And why is that? Well, the way electricity works, with alternating current, we've talked about this before, like a dynamic mic is basically a miniature power station or a power plant. You've got a coil of wire attached to a diaphragm that is very sensitive to vibrations in the air, and so when I speak into the mic, it moves. And inside of that coil of wire is a magnet, and as the coil of wire moves around the magnet, it generates a voltage, which creates electricity. But voltage is just sort of the force that pushes on the electricity to try to get it to come out of the mic. It's not actually going to go anywhere unless it has a place to go. And where does it want to go? It actually wants to come straight back to the source on the other side of that magnet. So you need a complete circuit to get current moving. You need a wire that comes out, and you need a wire that comes back. You need 2 wires. One wire is called the hot conductor. So that's the hot conductor is what carries the signal. And then the signal that carries it back, the return line, is called the ground. And ground is kind of a confusing subject because there's actually like 3 or 4 different things in audio and electrical engineering that are called ground, and they're all different, and it can get kind of confusing. But when we say ground here, when we're talking about audio, that's the return path. That's what completes the circuit so electricity can get moving in the first place. So unbalanced cable, you have those 2 lines. You have the hot conductor and you have the ground. Now, the ground wire, for safety reasons, is actually attached to the outer chassis of the microphone. And when you connect it to a speaker or some other kind of device, the ground is also attached to the outer chassis of this. So there's actually current flowing through this and this as I touch it. And that's actually for a safety reason. It's completely safe. It's actually safer when you do that because, and I don't want to get too deep into this because this is where it gets confusing with the word ground being used in different ways. But on your electrical outlet, where you have those 3 different lines, and you have like, the 2 conductor, you have a hot conductor and a neutral, and then you have a ground. Well, that ground is also attached to the chassis on your devices. And what that does is if there's some kind of a short where like the hot conductor on the inside of this comes loose and touches the chassis, if that happens, well now there's 120 volts, 20 amps of current flowing through this. And if I touch it, I'm going to get electrocuted. But because the ground, that 3rd pin on the outlet is also connected to the chassis, that provides a very low resistance path for it to go back out to the power plant. So the electricity prefers to go through that rather than my hand. So even though I'm touching it, it's going to escape through that ground. So now the reason why the ground wire on a microphone or any kind of audio cable is also attached to the chassis is so that if there's some kind of a short that would energize the microphone, well, it will also go through that same ground back out to the power plant. So it's a safety mechanism, having the ground tied to the chassis. But there's a problem. When you have the ground from the audio attached to the chassis, and you also have the ground from the electric outlet attached to the chassis, well now the audio system is tied into your electrical wiring. And so you can get a ground loop where the current coming out of the outlet decides it wants to travel from one audio device in your system to a different audio device in your system. And so it uses those connections between the ground and the different chassis to travel through. It's perfectly safe because, again, if anything goes wrong, it's just going to go back out the ground to the power plant. So you're not going to get shocked from that. But because that's part of the audio signal, remember that signal goes out and it comes back in on that same line, you can get a buzz from the power traveling from one device to another device. So that's one of the disadvantages of using an unbalanced cable where you just have two wires. It's tied into the electrical system, and so you could get a ground loop buzz. So that's why we have balanced cables, which have three wires. Let me explain how this works. It's probably easier to explain with a visual that stays there after I'm done. So we need to talk about a subject called phase, first of all. So I'm going to draw a sine wave. So there you go. There's a pure tone, a sine wave. And then I'm going to draw another one. Let's pretend that these are the same wave, but this one is a little bit behind that one. So these are different phases. It's the same wave, the same signal, but they're out of phase with each other. Now where's my eraser? I think it fell. I'll just use my finger. If they are completely out of phase with each other, where every peak is instead a trough, and every trough is instead of peak, if they were to collide with each other, they would cancel out. Phase cancellation. So what happens with a balanced cable, you actually have two different wires, which you can see here, the blue and the white one. You have two different wires, two hot conductors. And they're actually called hot and cold to differentiate them. And one of them is on one side of the magnet, the other is coming from the other side of the magnet. So you have the same signal going through two different wires. One signal has it hot, positive polarity, positive phase. The other is flipped upside down, but it's the same signal. It's just one is flipped. And then when it gets to the other end, to a device like this, it goes through what's called a differential amplifier, which takes this bottom one, the cold signal, and flips it back right side up. Now, why in the world would you do that? Why would you flip it upside down if you're just going to flip it right side up again when you get to the other side? Well, it's because as the cables travel through the wire, they're going to pick up noise. It's impossible to completely eliminate noise because it comes from all over. It comes from outer space. It comes from cell phone towers, radio signals. It comes from the electronics in the devices themselves. So it's impossible to completely eliminate noise. But what happens here is these two signals pick up noise, and because they pick up noise after the one signal has been flipped upside down, the noise is not flipped upside down. The noise is the same in both signals. So then when it gets to the differential amplifier and the code signal gets flipped right side up, the noise gets flipped upside down. And then when you bring the two signals together, the noise cancels. Phase cancellation. But because the two signals are now right side up, they combine and they actually get amplified. They get louder, twice the voltage. That's why it's called a differential amplifier. So that's the purpose of a balanced cable. And the ground wire, because it is external to this whole process, it's called an external line return, XLR. That's where the name comes from. So you got a hot, you got a cold, and then you've got an external line return. It still has a ground, but the ground is not, if there's any noise in the ground, like a ground loop or something, well, that's going to get canceled out through the same process because it's external to the whole signal carrying process. Now, the other thing the ground does, which you can see here, you'll see better when I actually make the cable, but I've twisted this up. It's coming off of this braid. It actually is this braid. It's a metal shield that wraps around the cables. So it's not actually a wire. It's actually a bunch of like metal braids that are tied together into a shield around those hot conductors. And then on either end, it gets twisted up into a wire. And what that does, that actually provides shielding from electromagnetic interference. Because there's a metal casing surrounding the wires and there's current flowing through that, that actually blocks out any sort of interference, or most interference. If you have some stray signal from outer space or something, it'll bounce off of that. It won't get through to the inside. So the ground actually serves a double purpose. It's an external line, so it gets filtered out in that differential amplification process. It's also a shield. It blocks out noise. And there's a third thing it does. This is actually what carries phantom power. So when you have a condenser mic or any kind of equipment that is powered by phantom power, like an active DI box maybe, if it doesn't have batteries, or if there's a microphone with a built-in preamp that's phantom powered, when you turn on that phantom power switch, it actually travels through this braid to the device. So it does three different things, but the main reason that it's called a balanced cable is because of this process, because of the way that the noise cancels out when you have these two signals with one reversed and then flip back on the other end. So that's how an XLR cable works. Now let's learn how to make one. First, just a few safety things. Do not touch the iron when it is hot. I actually burned myself last night doing this, so it wasn't too bad. There's like a little blister there. I don't know if you want to see that in the camera, but anyway. Don't touch the iron. Now, the reason that I touched the iron was not because I was like, hey, I want to touch that iron and burn myself. I did it accidentally. My thumb just kind of, as I was in the moment, came up over this hilt and touched the iron there like I almost did by demonstrating how not to do it. So yeah, just be careful not to accidentally touch the iron. Keep your finger below that hilt. That's what it's there for, to keep you from touching it. If you're about to solder something and then you decide, oh, I need to adjust it, don't keep the solder in your hand as you're adjusting it. Always lay it aside when you're not using it, and then do your adjustments and then take it back up again and then lay it aside. You also don't want your power cord to accidentally touch the solder or this thing in case that gets hot. That could be very bad because you could burn through the jacket here and expose the copper and electrocute yourself or start a fire. So that wouldn't be very good. So yeah, don't do that. And now we will make a cable. The first step is actually the hardest, and that is stripping the wire. The actual soldering itself is not very hard, but stripping the cable is a little tricky because as you just saw, there's all this little stuff in there. So we have to cut through the jacket, the rubber jacket, without cutting any of that if we can help it. We don't want to breach the braid at all or cut any of those wires. So you have to apply just enough pressure to get through the jacket, but not so much that you cut anything else, and then you pull it off. There's lots of different ways to do that. You could take a utility knife and you can kind of saw through it, and as you saw through it, you'll know when you hit metal. You'll feel like this grinding against the braid. That's a good way to do it. It's actually a great way to do it because it's very precise and controlled. So that would be a good method to learn. I'm going to show you a different method just because this can be a little more tedious. It can take some time to really get it in there and saw through it. And you can also cut yourself. And I don't want to cut myself today on the camera. I already burned myself last night. So I'm going to teach you a different method using a wire stripper and actually this part right here, which is for cutting cables. It's a little harder. It's harder to get a good clean cut, but I like this method. And actually, it's even better if you can get one that has like a curved cutter. This one's a straight cutter, but if you can get one with a curve that fits around the cable, that's even better. So I'm just going to take like 1.5 inches thereabouts and squeeze a little bit, and then kind of rotate the cable and keep squeezing. I might pull it a little bit it so I can see if I cut anything inside. I can see the braid and it doesn't look like I broke it at all. And then this is the part where it can go bad, because as you're trying to pull it out, you might accidentally apply too much pressure. If you can do it fast, it comes out pretty easy. Kind of like pulling a sheet out from under dishware. If you do it fast enough, it just comes right off. It can be hard to get a good grip on it. There we go. There's the jacket. And it's pretty clean cut for the most part. I did cut a little bit of the braid there. So it's best not to do that. Just for this demonstration though, I'm not gonna start over. It's not too bad. So then the next thing we need to do is unbraid the shield. And the best way to do that is to take something has like a small blunt point, like a little screwdriver like this, or you could get like a little hook or something. You could try a knife, but the knife might be just a little too sharp, not blunt enough, and you might accidentally cut something that you don't want to cut. So I like doing a blunt point like this, like a little screwdriver. And I'm just gonna kind of follow the braids with my eyes and see where it gets to the top, just that top braid there. And I'm just gonna stick the screwdriver in and push up, just like that. And then just keep doing that, keep working my way down. It can take a little bit of time, that's okay. And you want a good amount of it, because we can always trim it down later. But you always want to strip more than you need and unbraid more than you need, so you have plenty of room to work with in case you make a mistake. Also, when you decide how long the cable is going to be, like if it's going to be 20 feet or something like that, I would add like an extra inch on the end. So if you make a mistake, you still get your length in, and you can start over. Clip a new thing off. So I'm just going to keep pushing this in and unbraiding, working my way down. It's metal, so it's going to offer some resistance. And it's tightly braided, which is good, because that makes it nice and sturdy. Not every XLR cable has a braided shield. Some of them, it's just loose copper that's wrapped around to shield the inside, the conductors on the inside. But braided is actually better for live sound because it's stronger. And so it can take more abuse when you're doing quick setups and you're constantly unplugging it and plugging it back in. It's a little more expensive in the studio. If you're in a recording studio, you don't need braided shields as much. You can go with unbraided shields because it's not going to take as much abuse. It's just going to sit there most of the time. That might be enough. So I'm going to bunch this up. We don't want any of the wires ultimately touching each other, so I'm just being careful to take all these little hairs and bring them all over to the same side. The other thing that's in there is cotton. It's not always cotton, sometimes it's a different material, but that's just what that does. It helps insulate the wires from each other if there's a break somewhere, but it also provides some strain relief, as it gets pulled and tugged. We don't need any of that cotton, so I can actually cut that cotton off. And once you have enough, I could do more, but I'll go with that. We'll see how it goes. You just twist it up nice and tight. I actually, if you look at this one, I didn't do a great job. I didn't twist enough. They're not quite touching, but they're kind of close. It's functional, but this is going to fail sooner than if I had twisted it better. So you want nice, tight twists. Really turn it into a wire, not just a bunch of loose hairs of whatever this is, nickel. It's like a bunch of different metals. So there we go. There's our ground wire, our braid, our external line return. There's some loose hairs here. I'll just cut those off. We don't need those. And this can take a little bit to heat up, so I'm gonna turn this up now. It's on, but I just have it down to 1. I'm gonna turn it up to 4. That works pretty well. And while that's heating up, I'm gonna take these wires. You'll notice, I said that there's 3 wires, hot conductor, the cold, and then the ground, but you see 4 here. This is called a quad core cable. So instead of 1 hot conductor and 2 cold conductors, you have 2 hot, which are usually the blue, and then those get tied together into 1 cable. And then you have 2 cold, and those also get tied together into 1 cable. It's just for redundancy. It's a more reliable cable when you have more cores carrying everything. If something goes wrong, well, you have another core there. So that's also good for live sound when the cable might take a lot of abuse. Now this is where it gets really tricky because it's really thin wire, and we have to do the same thing with this. It's better to, I should actually do this on the plate because I'm getting all these hairs on the table. And this is what the plate is for, to catch solder or copper hairs. So I'm going to do it over the plate. It's better to apply too little pressure than too much, because if you do too much, then you have to start over, you have to clip it and do it all over again. But if you apply too little, well, you can just keep applying more pressure until you find the sweet spot. So that was too little pressure, so I'm going to apply just a little bit more this time. And that was just enough. There's the copper, and I'll do that to the next one. Too little, get a little bit more pressure. Still too little. And there we go. It actually doesn't technically matter which color you do as the hot or the cold, because there's a saying electricians have that electricity is colorblind. It doesn't know the difference between the white wire or the blue wire. It just flows wherever you put it. So you just want to be consistent. If I make blue hot on one side, then I need to make blue hot on the other side of the cable. And it is good to follow convention, so if somebody's repairing the cable, they don't have to examine the pin out and try to figure out which is which. They can just look at the colors. So it is good to follow traditional color schemes, but it doesn't technically matter. I have a little more excess cotton here, so I'm going to cut that off too. All right, where to go? There it is. So now I'm taking the blue, and what I'm twisting is not the blue part, I'm twisting the copper at the top. Twisting that into a single wire. Again, twist it tight because you don't want hairs hanging out that could touch the other conductors. That would not be good. And I'll take these white ones and twist these together to form a single wire. That looks pretty good. We don't need all of that. I'm not going to trim off a whole lot, but I'm just going to cut just a little bit. I'll just put them together like this. That's good. And now comes the soldering. So these are called helping hands. They've got a little magnifying glass. It's helpful for holding things. I actually haven't perfected the use of it yet, so I often just end up not using it. We'll see what happens in this video. But I'm going to start off using it. It's not real great to breathe in the fumes of the soldering. I mean, if I breathe it in today, I'm not going to die. But over time, if you do this a lot, some people do it for decades and they're okay. There's no health issues, but everybody reacts a little differently. So it's best not to breathe in the fumes. You can get like a little fume extractor that has like a fan and a filter, and you set that down here and it'll suck up the fumes and purify it. I don't have one here today. But another helpful thing about the magnifying glass and the helping hands is I don't have to get so close and potentially breathe in the fumes. Now, if you didn't know what solder is, this is it. This is solder. It's this metal thread that is mixed with this flux rosin core, which is the substance that makes it a little more fluid, gives it a lower melting point. So when you apply heat from an iron, it melts quickly. And when you take the heat away, it cools very quickly. So that's why this is used to join electrical components, because you can get some solder on it and then take it away. And then when the solder cools, the components are joined because the metal has solidified. So that's what this is. And then this is just to heat it up. You don't actually want to get solder on the tip. So what I'm going to do, hopefully we can capture it on the camera, but if it's hard to see, what I'm going to do is I'm going to get the solder underneath the wire, and then I'm going to get the iron underneath the wire, and then the solder on top of the wire, so they're not actually touching. And then the iron is going to heat up the wire, which will then heat up the solder, and the solder will melt onto the wire. And then I take the solder away, and I take the solder away first, and then take the iron away. And I let it cool, and then I do the next one. Solder underneath, iron underneath, solder on top, solder melts, pull the solder away, pull the iron away. And the reason you want to pull the solder away first is because you don't want this to cool and get stuck on the wire. So this goes first, then the iron. And we have our connectors here. I forgot. It's actually better before you even strip it, which I already did, it's better to get the connector on there. See if I can get it on anyway. This is a strain relief. So you've got strain relief inside from the cotton, and then you have strain relief on the outside with this thing. I actually don't know how it works, but strain relief. And this is the strain relief for the other conductor. And yeah, I guess we're doing female first. So I'll attach that there. There's mnemonics that you can memorize to know which goes where. I haven't memorized them, so I don't know which goes where, but it does tell you. It has them labeled. When you look closely, it has like a 1, a 2, and a 3. 1 is always ground, 2 is hot, 3 is cold. So I'm going to do the ground on 1, and then the blue, which came undone. I'll have to twist that again. I'll do the blue on 2, and then the white on 3. Yeah, I think I'm gonna hold this one by hand, and I'll let the helping hand hold the connector. I think I'll do that. So I'll do the ground first. Ground is this one, 1. Hopefully this stays. Maybe I'll try to get this. Just gonna kind of move it into that tray there. Oops. Something like that. And then soldering iron goes underneath, and then solder goes on top. So actually it's better to do it the other way around. So I can lay it down inside that tray. That's 1. And I forgot to do something. You're supposed to tin the wires, and you're supposed to tin the connectors. What that means is you get solder on them first, and then you solder them together. So let me do that first. So I'm gonna tin this. Get it nice and hot. Don't have very steady hands. Might just need a little more time to heat up, or I might need to turn up the temperature. It does feel hot when I touch it. Yeah, I'm not sure why it's not working. Get a different angle on there. Always lay it aside before you adjust anything. Oh, there we go. Now it's melting. Yeah, there we go. It's working. So, got some solder on there. And just in case any solder got on the tip, hit that in the trash can, clean it off on the sponge, get that nice sizzle. Stick that back in. Yeah, so we got that tinned, and then we'll do the hot. Same thing. It's a little smaller. Let's see if I can get a better angle. Get my elbow on there so my hands don't shake so much with the fine point. There we go. So we got that tinned, and then you can feel the heat when you touch the braid. It's not burning hot, but you know it does transfer down. That's another way you could burn yourself accidentally if you're touching something that the heat's going to radiate down. I'm going to try to get this one without touching the ones I already did, so I don't melt my work there. And there we go. So I tinned the wires, and then I'm going to tin the connector. That's going to cool very quickly. It's probably already cooled down and solidified. Lay that aside. I'll tin the connectors. Good way. Notice I'm not using a magnifying glass. It might work better for you, but I've never really gotten it to work. And I'm gonna go underneath the connector, get some tin in there. I can feel it radiating up here when I do that. It's cool now. You know, it's amazing how quickly it cools. Let's see if I can get under there. It's hard for me to keep it steady because it's so small and light. And it melts as I do it, so I'm trying to push it in and it's melting off. But yeah, I got some tin in there, and then I'll do the third one. Maybe it's better if I put the solder in there first and then come underneath. Yeah, there we go. Cool. So now I've tinned, laying this aside before I adjust anything. And actually, let me get the solder off. Now I've tinned my connectors, I've tinned my wires, and now I can make a good connection. Pin 1 is right there. I can get this arranged in a good way for me to work. just like that. So I can just sit it there and get the iron underneath and the solder on top. It's hard to get it to stay when I'm pushing on it from underneath. Let me push on it with the solder first and then come underneath with the wire. Might be hard to see what I'm doing on the camera, but this is just the best way for me to see what I'm doing. I'm going to try coming on top of this one. So get the solder nice and close there. There we go, now it's melting. And take it away, let it cool. And then I'm going to pull on it and see if it's a good solder. There we go. It's connected. And actually, let me see the pin out. The pin out is just like what each pin is. So this is 2 on this side, so that's for the blue wire. Move the white up here out of the way. And actually, it might be better to do the white first. It'd just be easier to not accidentally touch it with the iron. Or maybe it'd be better to do blue first. I'll do blue first. So I'm just going to get that. So you can see what I'm doing. I'm just going to get that in that tray there and then push it down with the solder and then get the iron near enough to it to get it to melt. So the solder on top, and then iron, and get it pretty close in there. And let that cool. Sizzle, sizzle. See if that's a good solder. Pretty good. The strain relief will also help with the tugging if it gets tugged on. And now one more. This one might be harder to get to stay there. Okay. Move this up a little bit. Rotate this. Just going to bend it so I can. Okay, that should work. Hopefully you can see that. And see if I can get this, get the tin on first, or the solder on first. And then it melts. Let it cool. There we go. We're all soldered. I'm just going to make sure there's no loose hairs touching the other conductors. Looks pretty good. Wish I could have twisted that ground even finer, but I think it is a little bit better than what I did there. Yeah, it's definitely better than what I did there. So yeah, that's good. That's functional. I already have these on, so I can slide these up now. This is called a noitric connector. There's basically 3 different types of connectors for XLRs. There's Neutrik, Switchcraft, and Canon, and those are just named after the companies that invented them. There's all sorts of knockoff companies that make their own style. This is a genuine Neutrik connector. Neutrik also invented the speak-on cable. And this tab is going to slide in to the locking mechanism. It actually goes this way because it screws on, the barrel screws on there. Actually, I probably should have screwed this side first because then I'm turning it inside. But as long as it holds together, it's fine. So there we go, there's a female connector. That's how you make an XLR cable. And then this is what the male connector looks like. So you're just going to do the same process, solder on those sides. There's no locking mechanism on the male, but just make sure you have the barrel on the right side so it screws in. And there you go. You've made yourself an XLR cable.